Okay, so let's get started with the week 10 session of Biomass Conversion and Biorefinery subject. The course coordinator for this course is Professor Kaustubh Mohanty from the Department of Chemical Engineering, IIT Guwahati, and I am Aryant Ahuja, your PMRFTF, who is working under the guidance of Professor Vibhor Kumar Stugi in the Department of Paper Technology, IIT Roorkee. So before moving on, let me tell you something about myself. I have done my MTech in packaging technology and now pursuing PhD in paper technology from IIT Roorkee and receiving Prime Minister Research Fellowship from the year 2021 to present on the topic of paper-based value-added products. So today we will discuss about the week 10 assignments of 2023 and we will then discuss some concepts related to the week 11 questions. So we'll start with the week assignment 10 of week 10, and you all have solved these questions in the previous week, but here I will tell you that what were the right answer and what was the concept behind those. So let's get started. Following which method is not dependent on light for biohydrogen production? So if we look at the question carefully, the question aims on the production of hydrogen gas in the absence of light. So it because it's written not dependent upon light, so absence of light. So if we look for the options now, the first option is biophotolysis of water using green algae. So biophotolysis is a technique in which photons are used. The use of photons are in the presence of sunlight. So obviously it's not the right answer because it depends upon the light. Next is photo decomposition or photo fermentation. So again, the word photo here says that it happens in the presence of photons. So it's not the right answer again. And third is dark fermentation. Dark fermentation means this process happens in dark, and the fermentation means it the fermenting process happens in the dark using some microorganisms. So this is a method which is not dependent upon light. Therefore, the right answer is dark fermentation. So the biomass can be converted into hydrogen via dark fermentation, and before this, there's a primary process which we do is pre-treatment hydrolysis, which helps to separate the cellulose, lignin, and hemicellulose from the biomass. And after the hydrolysis, we do the dark fermentation in the presence of microorganisms. These are some typical microorganisms which uh, do the fermentation in the absence of air. So this is mostly anaerobic fermentation and in the absence of light. And during this, two things are produced. First is hydrogen, also known as biohydrogen, because it is produced by biological ways. And second is the we get is organic acids, which can again be utilized for some other applications. So dark fermentation is a biological process in which organic waste or energy crops are converted into hydrogen gas. So we have seen that what we are doing, we are converting the organic waste into hydrogen gas using a fermented bacteria without the requirement of light. So it is called dark because it does not rely on photosynthesis or light. Therefore, the other options of photons, photo decomposition, were not the right answer. And dark fermentation typically involves the breakdown of complex organic compounds through anaerobic fermentation by bacteria, producing hydrogen gas, CO2, and organic acids. So, hydrogen gas is the primary uh, gas which we get. It is the primary fuel which you are getting through the dark fermentation. Then is the organic acid, and some amount of CO2 is also released during this anaerobic fermentation. So dark fermentation has an advantage of being able to utilize a wide range of organic waste materials such as every type of feedstock can be used, every kind of residue, food waste or wastewater, because we are just utilizing we just take the waste and do the pre-treatment, separate the components of the lignocellulosic material and then do the fermentation. with the help of microorganisms. So any kind of raw material can be used for this process. Now moving on to the next question. The major enzyme needed for the direct biophotolysis of water is, so there is a process uh, where the some type of enzymes are used to generate no, sorry, some types of enzymes are used to break down the water into oxygen and hydrogen in the presence of some enzymes. This can be used to produce hydrogen, which is a very good fuel, a cleanest fuel, and most of the work internationally is being done on hydrogen fuel because it is the cleanest fuel ever we have seen. So these are the enzymes we can use, which can do this process, but one of them is sensitive to oxygen. So therefore that enzymes work in the presence of anaerobic conditions, or it is mostly oxygen resistant strain we use sometimes. So that is hydrogenase as a, so hydrogenase is an enzyme which is used to convert hydrogen into hydrogen and oxygen, and it is very sensitive to oxygen. So this enzyme does nothing is that it just the water is converted to oxygen and hydrogen with the help of hydrogenase. But during this process, the oxygen concentration is increased. So this hydrogenase is not very efficient because as the oxygen increases, the hydrogenase life decreases. So therefore, hydrogenase is not suitable for this. But some different oxygen-resistant strains are available, and also we can do this in the absence of oxygen, so that the amount of oxygen is lesser. So, hydrogenase is a major enzyme involved in the direct biophotolysis of water, a process where light energy is used to split hydrogen and oxygen molecules. However, hydrogenase is very sensitive to oxygen. It is very much sensitive to oxygen and can be easily inhibited by the presence of oxygen, which is a byproduct of biophotolysis. Therefore, in biophotolysis, it is important to create anaerobic condition or use oxygen tolerant strains. So the hydrogenase is oxygen sensitive, and the generation of oxygen in this process leads to inhibition of this organism. Therefore, oxygen tolerant strain are used for this process. Now let's move on to the third question. Which component is typically removed from biogas via the process of biofiltration? So, when we produce biogas with during the production of biogas, some kinds of gases are also produced which are very corrosive. So these corrosive gases are need to be filtered, and this filtration is mostly done by biofiltration with the help of microorganisms and enzymes. So this corrosive gas is mostly hydrogen sulfide. So hydrogen sulfide is the most corrosive gas which is formed during the production of biogas, and to utilize the biogas for further heating purposes. For further heating purposes, we need to remove the hydrogen sulfide from the product gas, and this is done by biofiltration. So typically, before going to the diagram, let me explain the theory behind it. Biofiltration is a biogas cleaning process. It is a biogas cleaning process that typically targets the removal of hydrogen sulfide from biogas. Hydrogen sulfide is a common impurity. It is an impurity in biogas, and it is produced during the anaerobic digestion of organic matter. So, yeah, hydrogen sulfide is a toxic and corrosive gases which can cause odor issues. So, the method known as biofiltration is used. And biofiltration, why the name is biofiltration? Because it uses biological ways to remove the hydrogen sulfide, such as microorganisms, such as bacteria and fungus, to convert hydrogen sulfide into less harmful compounds. So basically, in this process, the biogas is fed to the chamber, and in this, some microorganisms are there, and these microorganisms oxidize the H2S to H2SO4 and then to SO2 plus H2O. So during this process, the hydrogen sulfide is removed and we get a less harmful gases at the end, and therefore we get hydrogen sulfide free biogas. Now moving on to the next question. In dark fermentation, hydrogen production by strict anaerobes is usually performed by which bacteria? So we have seen that what is dark fermentation. Dark fermentation is a process in which um, we use absence of light. It is done in the absence of light, and some type of microorganisms are used to produce hydrogen gas from the biomass. So to convert biomass to hydrogen, we need some bacterias, and these bacterias work in the absence of oxygen and absence of light also. And this strict anaerobic bacteria are mostly Clostridium species. So, as explained in previous slides also, the biomass is treated with some chemicals to convert them into lignin, cellulose, and hemicellulose. These are then further hydrolyzed to form monomers, and these monomers are then fermented with the help of some bacteria or enzymes and fungus. And the most common is Constridium species. This bacteria ferments the monomers obtained from lignin, cellulose, and hemicellulose, and in the absence of oxygen and in the absence of light, to produce hydrogen. And some amount of organic acids are obtained, which can be used for further application for some other applications, and some amount of CO2 is also generated as a byproduct. So in dark fermentation, hydrogen production by strict anaerobes is typically performed by Clostridium genus. These species are strict anaerobes, meaning that they can thrive in environment with little or no oxygen. So anaerobic, these are anaerobic, and anaerobic means no oxygen. So there are two types of, one are anaerobic and other are aerobic. Aerobic means they thrive with the presence of oxygen and they thrive in the absence of oxygen. So these species are capable of fermenting organic substance such as carbohydrate through anaerobic metabolic pathways and result into hydrogen gases. So the biomass is converted into monomers such as carbohydrates, and this is fermented with the help of this species to convert it into hydrogen gas. So these species are commonly used in dark fermentation process for hydrogen production from various feedstock, and every kind of feedstock can be used, such as agriculture residue, food waste, and energy crop. We can utilize any type of any type of bio waste or biomass waste, and the generated hydrogen can be used as a clean and renewable energy source for various applications. Because hydrogen, what we are doing, we are just producing hydrogen because hydrogen is the cleanest fuel which is ever known to us till now. So now moving on to the next question. The microorganisms, especially the methigenic bacteria. So as we go on the name, methanogenic bacteria are those bacteria which are used to produce methane, and this with acidogenic and acidogenic, which are used to produce acetic acids or butyric acids, and these are used to produce some other solvents. So these three bacteria, when they combine, they form a very big colony. and they thrive together. They all live together, and they cover the upper part of it with a very thin film in order to protect it from other. And these all bacteria live in a colony. This colony is known as biocenosis. So the correct answer for this is biocenosis. So microorganisms involved in the anaerobic digestion process, including methogenic, acetogenic, and acidogenic bacteria, form a biocenosis. And what is this biocenosis? It refers to the community or constituent of different microbial species that live together in a particular environment and interact with each other. They live just like they don't are not considered enemies, and they live together. So in this case, they form a very thin film. These typically form a very thin film known as biofilms on the solid surface of floccules, which provide favorable environmental growth conditions for their growth. And this is known as biogenesis. Moving on to the next question, which is the predominant macromolecule in biomass that cause the production of more ammonia in biogas? So when we look at the options, there are four different options here. Sorry, uh, there are four different options here. So fatty acids are what? They are COH, and R is a very long or very medium chain CHCC chain, carbon carbon chain. Carbohydrates are uh, 5 to 6 carbon ring, and it is also filled with CH and O. What are lipids? Lipids are oily, and these are produced by mostly microalgae, and these also don't have any type of ammonia. When we look at these three options, none of them have nitrogen in it. And when we look at the proteins have NH bond in it, and this NH bond can be used to convert into ammonia. Therefore, the answer is protein, because the question was which macromolecule in biomass cause production of more ammonia. So ammonia formula is NH3, and therefore the answer for this is protein. So during the anaerobic conversion, when this process happens in the absence of oxygen, the proteins are acidified, and then amino acids are formed. And these amino acids, proteins are typically NH, and amino acids are something which has amines and carboxylic acids. So the combination of amines and carboxylic acid are formed during this process, and these amines are converted into ammonia and some other products such as volatile fatty acids, hydrogen and CO2 and other things. But basically, only the presence of protein can be converted to the ammonia. Therefore, the answer was ammonia. So, protein is a predominant macromolecule in biomass that cause the production of more ammonia in the biogas during the anaerobic digestion process. Protein are complex organic molecules composed of amino acids, and their breakdown during anaerobic digestion results in the release of ammonia. This ammonia can accumulate in biogas and have adverse effects on its quality and usability. Therefore, the ammonia gas must be removed from the process. But we do not remove the ammonia from the afterwards. We remove the protein from the mostly from the biomass. So if the biomass has protein in it, we will remove this protein in the starting only, so that ammonia formation is not happening, because ammonia can have adverse effect on the quality and usability, such as increased corrosiveness and decreased energy content of the biofuel. Therefore, proper management of protein-rich biomass in biogas feedstock, such as adjusting the carbon-nitrogen ratio and maintaining optimal operating conditions, should be done. But other than these, we should just remove the protein from the biomass by doing the effective pre-treatment method. So, in next question, in dark fermentation, hydrogen production by facultative anaerobics is performed by which bacteria? So, we have seen that the different types of bacteria also, that Clostridium was strictly anaerobic conditions, but there's another which is known as enterobacteria species, which produce hydrogen by facultative anaerobics. So in this, these bacteria particularly are capable of producing hydrogen under anaerobic condition, but they can also tolerate and grow in the presence of oxygen, making them facultative anaerobics. Facultative anaerobics in this, if there is a presence of oxygen also, they can do the reaction and make the hydrogen from the biomass. So they need anaerobic conditions, but they can also work in aerobic conditions. So they are known for the ability to ferment various organic compounds, including carbohydrates, and produce hydrogen gas as a bioproduct. Tar fermentation using facultative anaerobic bacteria is a promising approach for hydrogen production from biomass, and it allows the efficient hydrogen production without the need of strict anaerobic conditions. When we have seen that in Clostridium species require strictly anaerobic conditions, but this bacteria does not require strictly anaerobic condition. Some amount of oxygen can be present in the environment also. So, which microalgae has been extensively researched for indirect biophotolysis for biohydrogen production? So, the answer for this, Chlamydomus rendaris is the mostly researched microalgae which has been used for indirect biophotolysis. So it is a microalgae that it is a unicellular green algae that can undergo both photosynthesis and fermentation, allowing it to produce hydrogen gas under certain conditions. So we do not require two different microalgae because in most cases we do photosynthesis by some microalgae and then produce hydrogen by some bacteria. We need two types of microorganisms, microalgae and bacteria. But this particular species of microalgae can do both the things. It can do photosynthesis also and fermentation also. So therefore, this is the most researched microalgae to produce hydrogen gas, and therefore it has the potential in producing biohydrogen, and this process is known as biophotolysis, where hydrogen gas is produced from water using light energy. So this is basically nothing but water is converted into oxygen and hydrogen in the presence of this algae, and this algae works with on the in the presence of light. So it is not like dark fermentation, which happens in the presence of darkness. So this microalgae has been genetically engineered to enhance its hydrogen production capabilities and is considered a promising candidate for biohydrogen production from renewable sources. So moving on to the next question. In 1956, Jasubhai J. Patel developed a design plant popularly known as gas plant. So in 1956, some digesters known as floating drum digester were made. What these digesters do was, if the production of gases is higher, the digester would float and go upward, and when this gases comes out, it would go down. So it was known as floating drum digester. So this digester adjusts itself up and down with the concentration of the gases, and this was used as a to produce gobar gas plant, and in India it was a very popular technique to produce biofuel, and outside India also the world has also adapted in nearly the in 1960s, but during the 1970s The Chinese introduced fixed dome digesters, which were very cost effective, and these cost effective fixed dome digester replaced the floating after the 1970s. So, Yashubhai Patel developed a design of floating drum digester plant, which is now popularly known as Cooper gas plant, and this uses a floating drum to collect and store biogas produced from organic waste. And this floating drum, this floating drum floats, so it rises and falls. It goes up and down depending upon the gas pressure inside the digester. So if the gas pressure is higher, it will go up and down, and thus it can optimize the uh, collection and is very efficient for storage of biogases. And this process, floating drum digester was adapted very widely in India and other countries for small-scale biogas production, particularly from animal dung and other organic waste materials such as renewable energy for cooking, lighting, and other applications. But this was then replaced by fixed dome digester because they were very cheap, and so the cost was reduced. Therefore, these were replaced in 1970s. So this is what floating drum digesters look like. So this is a gas holder, and this thing goes up and down and it depends upon the pressure here. So this is a typical floating drum digester diagram. So moving on to the last question of assignment 10, and which raw material is utilized in the convection process to produce methanol? So methanol are produced by very various ways. There are numerous kinds of ways to produce methanol, but there is a one common and most conventional oldest method to produce, and that was utilizing the natural gas. So natural gas. So before moving to this, I will explain the theory. Then I will come to this block diagram. So methanol is also known as wood alcohol, and its chemical structure is CH3OH. It is the smallest carbon chain alcohol, and it can be produced by natural gas, coal, syngas, and different kinds of biomasses. However, the conventional process for methanol production primarily relies on natural gas. The conventional process was using natural gas as a feedstock. And what is natural gas? Natural gas is composed of methane, and therefore this can be converted into methanol very easily. So this was a very common source of methanol, and due to its abundant availability and relatively low cost, it was widely used. So natural gas is a typically converted into syngas. What is a syngas? Syngas is a mixture of hydrogen and carbon monoxide. So methane in this, the natural gas is converted into syngas through a process known as reforming. So reforming is a process to convert natural gas into uh, syngas, and then this syngas is further processed to produce methanol through a process known as methanol synthesis. This methanol synthesis is done in the presence of catalysis also. So, and this methanol can be used for numerous applications such as to production of chemicals, plastic, formaldehyde, or as a clean burning fuel in fuel cells or internal combustion engines. So the natural gas is mostly composed of methane, and this methane is then converted into syngas, which is carbon monoxide and hydrogen, and this again is converted into methanol with the help of catalysis. During this, many other different products are also formed, and these products can be distilled and so that we can get a purified form of methanol. And during this process some kind of hydrogen is also left over. So this hydrogen can be used can be recovered and used again as a clean fuel. So we get some amount of hydrogen, methanol, with the help of natural gas. Therefore this was the most convenient and method because we get two different types of fuels. Now these questions, week 10 questions, were you might have solved these in the last week, and for the following assignment, for the week 11 assignment, I will share some preparatory concept which will help you to solve the week 11 assignments question. So biomasses can be generated into fuel, and we have seen that these can be generated into fuel such as ethanol and diesel or bio oil with pyrolysis and different kinds of things. But these biomass can also be converted into olefins and low molecular weight olefins. And how can we do it? This can be done by pre-treatment of biomass and such as combustion, gasification, pyrolysis, or liquefaction. So combustion means to in combustion a temperature of more than 800 degrees Celsius is applied, and this combustion can be used to generate heat and power, which is a simple utilization of biomass. But other than this, if we want to produce olefins, what we can do is we can do the gasification of it, gasification of pyrolysis or liquefaction. In this process, we get is what is known as fuel gases. In all the process, we get is fuel gas, and which is sometimes bio oil, which are very thick oils obtained from the high temperature pyrolysis. Also, we can get char, which is obtained from low temperature pyrolysis and different techniques. And these can be again converted to monomers such as methane or liquid biofuels or some small chain olefins. So, what are these processes? But what is this gasification, pyrolysis, or other techniques? So, in gasification, biomass is heated in the presence of gasifying agents such as air, oxygen, or steam. So the biomass will be heated in the presence of some type of gas. And this gas can be air, oxygen, or water vapor, also known as steam. And this can be used to produce synthesis gas or syngas. And what is synthesis gas or syngas? It is CO plus H2. So syngas can be further processed to produce light olefins. So this syngas can also be produced to convert into light olefins through a catalytic or chemical reaction. For example, syngas can be passed over a catalyst to produce ethylene. So CO plus H2 can also produce ethylene or propylene or butadiene, which is known as Fischer-Tropsch synthesis or through other catalytic process. The second is pyrolysis. So pyrolysis involves the thermal decomposition of biomass in the absence of oxygen. We know that pyrolysis of many things can be done to produce some kind of bio oil or biofuel or gas and char, different types of fuels which we can get at different temperature. At high temperature we get good quantity of oil, and at low temperature we get higher quantity of chars. So this bio oil in this process, this bio oil which we get from the pyrolysis can be converted to light olefins or BKs through catalysis process. In a similar manner, combustion, which is simple burning of biomass in the presence of oxygen, gives us heat energy, and it is primarily used for generation of heat and power, but it is also utilized for the production of light olefins or BTEX through gasification and pyrolysis, as we have discussed before in the previous slides also. And finally, the liquefaction process. Liquefaction involves the conversion of biomass into liquid product in the presence of solvent or liquefying agent. And this liquefaction process can also produce bio oil. And this biooil can be converted to olefins in the presence of catalyst, as we have done in the pyrolysis process. So all these processes produce some kinds of oil, but or some kind of fuel, and these fuels can be converted into olefins via catalyst. And these olefins can be used as a starter material for other things, such as the ethylene, which we get from the syngas. CO plus H2, when we were using syngas as a material, this syngas can be converted into ethylene. And this ethylene is a olefin. And this ethylene can be used to generate polyethylene, which is a polymer. And therefore, these olefins also have a very good industrial usages. Therefore, the use of biomass in fuel, the biomass can be utilized to produce fuel, but also some other chemicals which can be used in other industrial applications. So, other than the olefins, there is another category of product which we get is furfuryls. So, what are these furfuryls? Furfuryls are a class of organic compounds. These are organic compounds that belong to a furan family, and this are characterized by furan ring structure with an aldehyde bond, which is also known as CHO. So, in this diagram which you are seeing, this is CHO. This is there's a functional group CHO, and this is known as furan ring. So the presence of aldehyde on the furan ring is known as furfuryls. These it is a group of compounds, and they are majorly heterocyclic compounds consisted of five-membered ring containing four carbon atoms and one oxygen atoms. And these are found in very different types of foods such as coffee, breads, and roasted nuts. Furfural can be found in various types of foods, and they also have very good industrial applications such as resins, solvents, plastic, pharmaceutical, and flavoring agent. So these furfuryls are the starting material to produce all these um, additives. We can produce these things with the help of furfuryls. But in what stage do we get this? You might have remembered that in the I don't remember the correct week, but there in starting, the hemicellulose were once converted to monomers. So during this conversion, some byproducts were also formed, which were known as furfuryls. And these furfuryls used to cross-link with each other to form resins. So these furfuryls can be made from hemicellulose. And how we are getting this hemicellulose? We are getting it from the biomass. So furfuryls can be obtained from biomass through the hemicellulose when these hemicellulose were uh, made into monomers such as pentosanes. So these are the common furfuryls which we get. So hemicellulose, we do the hydrolysis of hemicellulose to convert it into smaller monomers. Hemicellulose is a polymer, a type of polymer, and we do the hydrolysis and break it into monomers such as xylose or arabinose. But during this process, uh, due to the insufficient uh, ways to do the reaction, some byproducts are also formed, and this byproduct is known as furfuryls. So, cellulose and hemicellulose both can form different types of furfuryls. Hemicellulose mostly form furfuryl, and cellulose form hydroxymethyl furfuryl. So therefore, furfuryls can be obtained from cellulose and hemicellulose. Therefore, we can get these from biomass, because biomass are firstly treated to separate them into cellulose and hemicellulose. So furfuryls are typically produced from biomass feedstock through the process of biomass conversion, such as thermomechanical or biochemical processes, which involve the degradation of transformation of biomass into furfuryl and other valuable chemicals. And these furfural can be again used for different application. And the most the important application of furfural is to produce different types of plastics or and resins, which can be used in adhesives. It is the most used application for furfural. So the generation of furfural, that why these are generating when we are making the when we are breaking the hemicellulose into the monomers, then why do we get furfural? This is due to the presence of water, and this process is known as cyclodehydration. So, first of all, what is this cyclodehydration? Cyclodehydration is a chemical reaction that involves removal of water from a compound to form cyclic structure. So, cyclodehydration comes from two words, cyclo and dehydration. Dehydration means removal of water, and cyclo means cyclic compounds. So, in this, the water is removed to form some cyclic structures. And in this process, when we talk in the case of hemicelluloses, it refers to conversion of pentoses such as xylose or arabinose into furfuras through the removal of water molecule from the precursor of pentosane molecule. So when we go in this reaction, in this, when the water is removed, when this OH and H is removed, we get is what is known as furfuras. So the removal of water from the xylose or arabinose, also known as pentoses. So the removal of water from pentoses results in the formation of furfural. And this process is known as cyclohydration. So cyclohydration is an important step in the synthesis of furfural from biomass feedstock as part of an overall process of biomass conversion to produce value-added chemicals. So we can control the dehydration process also, and it depends on very different reaction condition, and therefore we can obtain this monomers pentosanes. We can obtain both pentosanes or furfuras, whichever we want, uh, just by dehydrating it. So if we are getting pentosanes, and if our requirement is to obtain furfural, we will dehydrate it. But if we only need pentosanes so that we can produce fuel out of it, we will not dehydrate it, and we will do it in the presence of high amount of water. We will do this in the presence of high amount of water. So therefore, we can get pentosanes or furfuras according to our need by controlling the amount of water in the hydrolysis of hemicelluloses. So this is a typical section of hemicelluloses. What we do is we do the hydration, we do the hydrolysis of the hemicellulose. First we take the biomass, do the pre-treatment, we separate it into lignin, cellulose and hemicellulose. And this hemicellulose we do the hydrolysis to in order to break this very big compound into smaller compound. This is a big compound, and we break it into smaller compound, and thus we get xylose or arabinose. But during this, we can, if we take the water out, we do the dehydration, also represented as minus H2O here. We get is what is known as furfuras. And we can also make very different types of compounds from these furfurals, such as furfural alcohol or tetrahydrofurfurals or different furans and many other things. So therefore, the role of furfural is to produce different kinds of chemicals which have very different applications at in every different industries. So for now, I hope that you might have understand that how can we make furfurals from hemicellulose just by dehydrating the xylose which we were getting from the hemicellulose. So in this process, after we get the furfurals, we do the hydrogenation. If we do this hydrogenation, that is addition of hydrogen, we can get variety of things such as tetrahydrofuran or tetrahydrofural or furfuryl alcohol. And these are very the different types of solvents. These are very different types of solvents which can be used in very different industries. So this hydrogenation of phosphorus, when we did the hydrogenation of phosphorus, what we get was we obtain THF tetrahydrofuran, and we also get some type of alcohols which are known as THFA tetrahydrofuryl alcohol THFA. So these two things have very good usage as a solvent in different types of industries. So THF is a widely used solvent and chemical intermediate in various industrial applications, including as a reaction medium, polymerization solvent, and a starting material for synthesis of other chemicals. So in order to make THF, what we did was we utilized phosphorus. And how did we get this phosphorus? We got it from the pentosals. And this pentosals were obtained from hemicellulose, and this hemicellulose from biomass waste. So in this way, the biomass waste, which we see the wood or these things, we can create a very useful product or very useful solvent such as THF or THFFO. And these both are produced by the hydrogen of phosphorus. Another important compound which is used in industry is ascorbic acids. The L-ascorbic acids are also known as vitamin C. So vitamin C is commercially derivative of glucose that is primarily manufactured by chemical synthesis. And in this, the glucose, which is a monosaccharide or simple sugar, is a common starting material. So in the previous slide, we have seen that how we are getting THF furfuryls from hemicelluloses. And in this case, what we do is the biomass is we do the treatment of biomass. We get lignin, hemicellulose, and cellulose. And this cellulose is then we do the pre-treatment. We do the hydrolysis of the cellulose to obtain some type of simpler sugars, which are monosaccharide or mostly glucose. So the cellulose can be converted to glucose as we have seen in past weeks also, and this glucose are converted into ascorbic acids. So it happens in two steps, and major step is the oxidation step. So it involves multiple steps including oxidation, reduction, and other chemical transformation. And different chemical routes and methods can be used to manufacture ascorbic acid, and various synthetic approaches have been developed. So basically, first is to we what we have is we have a glucose which is a very straight chain material, and we convert it into cyclic form. And this cyclic we do the oxidation of this. During this oxidation process, this single bond is converted into double bond. This results in the formation of ascorbic acid or L-ascorbic acid, which is known as vitamin C. So in this way, the biomass can be used to produce vitamin C also. Third material which we had was we have discussed about the hemicellulose, we have discussed about the cellulose, and now we'll discuss about the lignin and uh, the applications of lignin byproducts. So first of all, how to isolate that lignin? We can take the biomass and do the pre-treatment to obtain pulp. So this pulp, after this pulping, we do the bleaching process and we remove the lignin so that we can get cellulose, pure cellulose. But in the solvent, if we are performing any pre-treatment such as organosolvent pre-treatment means the utilization of organic solvents such as acetic acid or ethanol, any type of organic acid, to treat the pulp and remove the lignin. So this organic solvent dissolves lignin, and in this way we can get a lignin dissolved solvent. And this lignin dissolved solvent we can just filter it or precipitate it. We can also precipitate it by some anti-solvents. Anti-solvents mean If lignin is dissolved in any mm, if lignin is dissolved in some solvent, then we will pour some another solvent in which lignin is not dissolved, which is known as anti-solvent. So this anti-solvent is poured into this beaker, and in during this process, lignin precipitates and settles down. And what we'll get is we'll get a solvent, and lignin will be at the bottom, which can then we can filter it on a filter paper and collect all the lignin. And lignin is a brown color, this sticky substance. So we can isolate lignin in this way. But why we are isolating lignin? We are utilizing cellulose and hemicellulose in biofuels and furans and producing ascorbic acid or vitamin C. But what is the role of lignin? So before going towards the role of lignin, what is lignin? So lignin is a very complex polymer. It is a very complex polymer. It is rich in OH bonds, and it also has some kind of ester and aldehydes. It is a very complex material, and it is present in the. It is a primary component of the plant cell walls, and it is a sticky substance. It binds the fiber, cellulose and hemicellulose. Lignin binds these fibers, and it protects it so that nothing can enter the fibers. So before producing any type of biofuel, we remove the lignin. So lignin also provides structural supports to plants and plays a crucial role. And this, after removing this lignin can be used for various kind of activities, such as adhesives, binder, dispersing agent, emulsifier, and even in cement and gypsum board manufacturing units. They are also used in various different kinds of applications such as oil well drilling, road stabilization formulation due to their properties such as high reactivity, water resistance, and binding ability. As I've told you earlier also that lignin is a very sticky material. So it is highly used in binding application or adhesive applications. Also, it is a hydrophobic in nature. It is water resistant. So therefore, it is also used in many hydrophobic coatings also. And the major thing about lignin is that it is obtained it is very abundant in nature. Lignin is the very abundant in nature. Firstly, we have cellulose. At second, we have chitosan, and at third, we have lignin. These are the most abundant polymers available in the environment. So lignin is at the third position, which is abundant in the environment. So, due to its abundance, renewable nature, and versatile properties, it is bio-based. It is abundance. It is very good properties. So, lignin has a very great potential in various types of industries, and is also eco-friendly alternative to very high synthetic material. In future, also we might see lignin-based materials coming in many industrial applications. So these are some summation of the application of lignins in very variety of applications. It can be used to to produce some different types of chemicals also, such as vanillin or DMSO, which are DMSO is a very good solvent which is used industrially, and it can also used to produce carbon fibers or carbon nanofibers. And as it is, we can also use to produce ink or dye from it as it is brown in color. It is somewhat brown to black in color, so we can produce carbon black pigment dye and different types of things. It is a very good binder also. It has a very good tackiness, so it can be used as a binding and as a adhesive. Therefore it can be used in the application of printing inks, mineral anima feed pellets, and produce thermoplastics also. Moreover, we can produce some kind of polymer also from lignin. We can do the polymerization of lignin with the help of urea formaldehyde, also known as UF, of phenolics, of furans. We can also utilize furans and lignin. We can polymerize these furans and lignin both to produce a new polymer also. And it can be used as an insecticide also. Therefore, it has a very good application in agriculture unit, and it has a It is a very good emulsifier, so therefore it can be used in roads, construction roads also. Which the construction road which we see is mostly made up of bitumen, and mostly you might known have it as asphalt. Some people call it asphalt, and some people call it bitumen. And during this bitumen or asphalt road, we can add some kind of rubbers or plastics in this road to make it to improve the aging of road. But these rubbers or these plastics get separated from the bitumen very easily. So in order to stabilize them, we can add lignin as a stabilizer, so that the plastic and the bitumen does not separate and the age of road is increased. Also, it can be used as a functional material in fire retardant materials such as textile, and therefore can be used for people which are working in fire extinguisher units, so that their clothes are not burned off. And it is also used as an additive material in many different polymers to improve its hardness or its compatibility. So it can be used in concrete, cement, polymer, composite. It can be used as a stiffening agent also. So we have seen that there are many different kinds of applications of lignin, and therefore lignin is a very good use, and it can be used as a very high use in industrial in future. Now we'll come to the next thing which is of important use and we obtain from the biomass, that is butyric acid. So butyric, it is a very short chain fatty acid. We know that short chain fatty acids, we have seen that it is mostly composed of long chain carbon, and at last it has a COH, carboxylic acid. But these were long chain. They were like C18, C16, or C12, and mostly they were we can get these from oils such as palm oil or soybean oil. But butyric acid is not a long chain fatty acid. It is a short chain fatty acid. It only has four carbon, one, two, three, and four. So it is a short chain fatty acid and can be produced by certain microorganisms through fermentation of carbohydrate. It has various industrial applications, including a precursor for production of other chemicals such as butanol, butyl esters, and butyl rubber. So, if we have some crops such as soya bean crops or palm crop, they are very much uh, rich in lipids or oils. So these lipids might also have short chain fatty acid. So these short chain fatty acid have butyric acid, and this butyric acid is used for the production of cellulose butyrate. Cellulose butyrate is a very good polymer which is used in industrial application, very much different industrial application. So first of all, but how this butyric acid we can get in more ways other than this. So we have seen about the Clostridium species earlier also, that we can do the dark fermentation with this process and obtain the hydrogen gas, and we can also get butyric acid from this. So how can we can get? So Clostridium is a species of bacteria that includes various species known for their ability to produce endospores, which are resident structure that allows bacteria to survive adverse conditions such as lack of acid. We have also seen that in it was a type of anaerobic bacteria and can produce hydrogen in the absence of oxygen. So some species of this Clostridium are also chemoorganotropic, meaning that they obtain energy by metabolizing organic compounds, and are strict anaerobic, which were used in producing hydrogens. So these generation of Clostridium, there are two more. Butyrobacterium and Butyrovivirium. These are the mostly these two types of Clostridium can be used to produce butyric acid, and this butyric acid uh, either we obtain from lipids or from the microorganisms. These butyric acid can be reactive with cellulose to form cellulose butyric. So what is cellulose butyrate? Cellulose butyrate is a cellulose ester that is formed by chemically modifying cellulose with butyric acids. So it is a type of thermoplastic material, and it is known for high transparency, excellent toughness, and good chemical resistance. It also has a wide range of application, including in the production of coating, films, fibers, and molded products. And cellulose butyrate is a cellulose ester where butyric acid is used as an acetyling agent. So the cellulose ring is reacted with butyric acid to form an ester. And what is this ester? It is a type of polymer, and this polymer is a very this polymer can be used as a coating or as a barrier material also. So therefore, we can utilize this butyric acids obtained from microorganisms or from lipids, and then react with cellulose to produce cellulose butyrate, which is another byproduct which can be used for industrial application. So this week was mostly about the uh, different types of byproducts which can be obtained during the production of biofuels, and how these byproducts can be utilized for different types of applications. One last is methanol, which you all might know that methanol, as we have discussed earlier, also this methanol can be produced from natural gas. Sorry, the natural gas, such containing methane, can be used to convert to syngas, and this syngas can be used to make methanol by the help of catalysis. But what is the use of this methanol? It is not a fuel. It is not a very good fuel. Uh, the natural gas is a fuel, but what about this methanol? So methanol has a very unique property that is known as anti-freezing agent. So it does not freeze at very low temperatures also. Therefore, it is used as an anti-freezing agent, that we mix this methanol in any type of solvent and then it will not freeze. Why? Because it has a very low freezing point of minus 96 degrees Celsius. It freezes at very low temperature, making it effective as an anti-freezing agent in various applications. That's why we make methanol out of various different techniques, and this methanol is sometimes also this methanol can also be made from natural gas, as we have discussed in previous slides. Also, methanol, if we dehydrate this methanol, we get another solvent which is known as methyl ether ethyl ketone, also known as MEK, and it is used as a solvent in various application, and mostly it is used in ink, to produce ink for packaging applications. So MEK is a common solvent used for dissolving ink, and during printing also it is used. And also it is MEK is added to gasolines to increase the octane rating. So uh, that's for today. And today, as we have discussed the previous week question answers also, which you have solved them, and we have discussed some concepts which you will which will help you all in solving the next week questions. And I hope these concepts will help you. If somebody has missed the slides from the starting or have came at the last, they can see the recorded version of this slide at the online version in today only. I will upload this. And if you have any type of question, you can always ask in the chat box, or if you have any kind of question in the future for the assignment 11, you can always email me, and I'm sharing you my email address in the chat box. I've shared the email, and if you have any kind of doubts, you can always contact me with this email. And in next week, we'll discuss about the week 11 assignments, the questions which of the next week, and discuss about some concepts of week 12. So we will meet you next week.